Good evening, everyone. Myself Sana Sheikh, a second year PhD student from IIT Bombay, and I'm going to take your live session of course named Symmetry Stereochemistry and Applications. And the course instructor is Professor Anshuman Roy Chaudhary from IISER Mohali. So, this is the week 5 live session, and in today's live session, we are going to discuss the previous year assignment questions of week 5. So before going to start, I would like to give a brief introduction of today's topic. Today we are going to discuss the asymmetric, symmetry, and disymmetric molecules and topicity of the molecules. The, we will discuss the question based on these topics. Let's move to the question. So the question number 1 is indicate whether the following molecules are symmetric, disymmetric, or asymmetric. So before solving the question, we should know the definition of these terms. What is symmetric molecules? Anyone? The symmetric molecule are nothing but the achiral molecules. A molecule is type of a molecule which shows a super superimposable with its mirror image, and symmetry axis and symmetry plane are present in those molecules which are called symmetric molecules. What is chiral molecule? Chiral molecule are non-superimposable with its mirror images and is applied to molecules conformations and as well as macroscopic objects such as crystals. What is disymmetric? Disymmetric is a synonym of chiral actually, but it's not equivalent to the asymmetric because disymmetric or chiral entities may present. Sorry for the disturbance. Yeah. So disymmetric are a synonym of chiral, but not equivalent to the asymmetric. And since disymmetric and achiral entities may possess CN axis, that's why it's called disymmetric. What is asymmetric? So asymmetric is a molecule which are lacking of all element of symmetry other than the identity or E element. So this classes belongs to the asymmetric class. I hope definition is clear to you. We will solve the examples, then it will be more clear to you. So first, in all the molecule, what we have to see? First, we have to check SN axis is present or not. If SN axis is present, then we have to check the chirality of the molecule. So SN axis is present, that means the molecule is achiral or symmetry. We can say symmetry. But if SN axis is absent, then we have to check the CN axis. So if SN axis is absent, that means the molecule can be chiral or it can be disymmetric also. So we have to check the CN axis. If there is no CN axis, that means it is a asymmetric molecule. And if any CN axis is present, that means the molecule is disymmetric. Okay. So let's move to the example. So this is the first example. So here you can see uh, this is a cyclobutane and 4 chlorine is substituted on each carbon. So we have to check it is symmetric or disymmetric or asymmetric. So you have to check the SN axis. Can you check the SN axis is present here? Any SN axis? Yeah. If you will see here, I is present, center of inversion. You can see here, this is the center of inversion. And here also, this is the center of inversion, right? That means here SN S2 axis is present. I is equal to S2. I hope all of you know this. So that means here as an axis is present, that means this molecule is achiral and it is symmetric. This molecule is achiral and symmetric. Achiral and symmetric. Okay. I hope all of you get it. We will solve more examples. So if we have I in center of inversion I and H2 axis, that then we don't need to check the superimposable mirror images. That means we don't have to draw any mirror images if we got the SN axis and I present in the molecule. Okay. Now let's talk about this molecule. This is a CH2. Here we have two hydrogens. So we have to check it is a chiral molecule or achiral molecule. Then we can find out symmetric, asymmetric, asymmetric. Then here you can see this group is same here. That means this carbon is achiral. Carbon is achiral because two same groups are present. There are no other four different substituents are present on carbon. That means it is a achiral carbon. Then we will pass the plane. If you see here, four bonds are there with this carbon. That means it's a tetrahedral geometry. But you will see here we have plane of symmetry, right? Plane of symmetry is present here, and C2 axis also. That means molecule is achiral. If any symmetry element is present, that means the molecule is achiral. So this molecule is achiral and symmetric. This is achiral. Okay. Now let's talk about this example. Here you can see here this carbon has four different substituents. Four different substituents, that means it is a chiral center. This molecule have a chiral center, one chiral center. Then now we have to check the SN axis and C2 axis. Here you can see here there is no SN axis present because if you will pass the plane, there is no plane here and no center axis of rotation is present here. That means it is a asymmetric molecule because here you don't have any CN axis present, right? There is no SN axis is present. That means it might be disymmetric or asymmetric. But here if you will check the CN axis, then we'll see that here there is no CN axis present. That means it is asymmetric molecule. It is asymmetric molecule. I hope all of you are clear. This is the asymmetric molecule. Let's talk about this example. Here this is a cyclopropane, disubstituted cyclopropane. Here you can see we have two chlorine group. So and one CH2 group. That means here we have two chiral centers. Here one and one chiral center is here, right? But when we'll see here, we can pass the plane here. Plane of symmetry is present, right? And axis of rotation is also present. If you will rotate by this on this axis perpendicular to the plane C2, sorry, plane of symmetry is present here, not C2 axis, only plane of symmetry is present here. And SN axis is also present here. Rotation followed by reflection. So because SN axis is present here, this molecule is asymmetric and achiral. Sorry, yeah, achiral. Symmetric and achiral. Symmetric and achiral. Because SN axis is present. Okay. You can cross check yourself by rotating this by C2 axis and then reflection. You will get the same image here you have. That means here SN axis is present. Now let's move to the next example. Here we have N-butane, disubstituted N-butane. Here you can see we have two OH group and here hydrogen is present. That means we have two chiral center. In this molecule we have two chiral center. That means four different substituents present on the carbon atom. So now we have to check it's a chiral or achiral. First we will draw in Fischer, which we have discussed in previous class. So Fischer projection. Then we will see it is a symmetric, asymmetric or disymmetric. Okay. CH3 and CH3 groups are present over here. And now we have to check. See, if we will rotate this carbon-carbon bond by 180, you will get this conformation this way, right? OH, then OH, correct? Where on if OH is present on wedge, that means it is on left side, and if it's present on dash, that means it's on right side. We have discussed in previous class. Okay. So now we got this molecule. We have to check here, is there any possibility of SN axis or not. So if we will see here center of inversion is present, correct? Here you can see. So, sorry for the sorry here center will not be present. Okay, I will write here. So we have to draw mirror image of this one. So if I will draw the mirror image, what I will get here? H will be here, OH will be here, then OH and H, right? If you will rotate this molecule by 180, what you will get? If you will rotate this by 180, you will get this OH this side and this molecule is this side, but this backside bond will come upside because this is backside this is present backside, right? So that means here no axis is present, no symmetry axis is present here, and inversion center is also absent. If you will pass the plane here, then you will not get the exactly mirror images. That means here plane of symmetry is also absent. As an axis is also absent. But if you will see here, these two molecules are mirror images of each other, but they are non-superimposable mirror images. They are not superimposable. If you Superimposable means it should be look like exactly what it has originally, but it is not superimposable. That means they are non-superimposable mirror images. They are enantiomers. That means they are enantiomers, and enantiomers are a molecule which has chirality, which has chirality. So these are enantiomers. But if you will see here if we will pass the axis from here, like imagine it's coming from down below side of the plane and coming towards our cell this way, and molecule is on plane of paper. Okay, molecule is on plane of paper, and axis is coming from back side of the paper and coming towards our cell. And we will rotate this by 180 degree, that means C2 axis. If you will pass C2 axis, we will get the exact uh, no indistinguishable indistinguishable image of this molecule. That means this is a there is C2 axis present. C2 axis is present. That means the molecule is disymmetry. Sorry, the molecule is disymmetry here. This molecule is disymmetric because C2 axis is present and there is no SN axis, no SN axis. And they are non-superimposable mirror images. That means they are enantiomers. Okay. Now let's discuss the next example. Here you can see this is the N-pentane, disubstituted N-pentane. So here again we will draw the Fisher conformation to find out the symmetry here, or we can directly do on this molecule also, because we can see here both the methyl group are going downside. Both the methyl group are going downside. That means below the plane. If we will see molecule from this side, then we can see these two OH group are on wedge. That means they are on left side, or we can simply draw it here. We no need to rotate the molecule by carbon-carbon bond, because both the methyl group is going same direction, going in a same direction. This is a CH3. Oh, not working. Okay, yeah, hydrogen. Then both the OH group are on wedge position. That means on left side. Okay, here you can see that here this is the center carbon of the center of the molecule. So here SN axis is absent because there is no I. No I is present here, inversion center. But here you can see that we have a plane of symmetry present here. Plane of symmetry, correct? If we will pass plane here through here, then we will get the same half of the molecule. That means plane of symmetry is present. And if we will see that if we will rotate it by C2 axis and then reflection, then we will observe the indistinguishable image of the molecule. That means SN axis is present. S2 is present here. Center of inversion is not present, but S2 axis is present here. Sorry. Here you can cross check it. Here plane of symmetry is present. That means, and according to the definition, there should not be any plane of symmetry or any element of symmetry present in the molecule for being it a chiral or asymmetric or disymmetric. But here we have plane of symmetric. That means the molecule is chiral and it is asymmetric. Sorry, it is symmetric. It is symmetric. Chiral, achiral and symmetric. Achiral and symmetric. The molecule is achiral if plane of symmetry is present. Plane of symmetry is here. Okay. If any symmetry element is present, then we don't need to check the mirror image of that molecule, because the mirror image will always show the enantiomer or diastereomer, which is only possible in asymmetric and disymmetric disymmetric molecule. But in symmetric and achiral molecule, we need to check only the symmetry element present in the molecule. Okay. Now let's move to the question number 2. Draw all the possible isomer of the following compound and determine which molecule will be optically active. So if we will draw this molecule in zigzag form here, first one I am writing here. How many carbon atoms are there? 1, 2, 3, 4, 5. Then 1, 2, 3, 4, 5. 5 carbon atoms. And we have acid group on terminal carbon. Both, we have 2 acidic group here. And on all the carbon atom we have OH group. All remaining carbon atom we have OH group. Correct? That means we have 3 chiral center. 3 chiral center, that means we have to do here, we have to follow this rule. According to this rule, this is a this 2n is a rule. According to rule, we are writing a 2n stereoisomer. That means n is nothing but the number of chiral center present in the molecule. So here we have seen here there are 3 chiral center. That means it's a 2n is equal to 2 cube, and which is equal to 8, right? That means there are 8 isomers are possible for this molecule. We will discuss each in detail. So I will write here CO2H group here, CO2H group here we have. Then one possibility is that all the OH group will be on wedge line. That means on front side. One possibility is that, right? What's the other possibility? I'm not writing CO2H group. Please understand those groups present on terminal carbon atom. And here one OH group is on front side. The second one is also on front side, but the third one is on back side. Correct? Third one is on back side. What's the third possibility? OH group will be on front side, the second OH group will be on back side, and the third one is on front side. If we will see in the starting compound, here you can see this chiral center and this chiral center have same substituent. So we will discuss later, but here we will get possibility of same isomer. So first I am writing all the possible isomer here, then we will discuss the chirality of those isomers. The third possibility is that here that both the OH group will be on back side and one OH group will be on front side. Correct? Then in similar way we have other four possibility, like all these three front side at carbon atom front side OH group can be go on back side, and we will get 3 dash confirmation. And here similar way we will get 2 dash confirmation of OH group, and third one is on wedge. So exactly different exactly mirror image we will get the other four isomer. But if we will discuss the chirality of the molecule, you can see here, if we will pass the plane here, we will get the exact mirror image of this half of this half of the molecule. That means here plane of symmetry is present in this molecule, first one. That means this is the achiral. If any symmetry element is present, that means the molecule is achiral and it is symmetric. So this molecule is achiral and symmetric. And when molecule is achiral and symmetric, that time the molecule shows no optical activity. That means it is optically inactive. Optically inactive. This isomer is optically inactive. Okay, inactive. Optically inactive. Now let's talk about the second one. So here, if we will pass the plane of symmetry from here, so it's not possible because it's on wedge side and this one is back side. So here plane of symmetry is not present. Now let's check the different other symmetry element. So if we will rotate this molecule by 180, then we will not get the non-distinguishable image of the molecule. That means here CN axis is also absent, and if CN and plane of symmetry is also absent, we will check SN axis, and here SN axis is not present. SN axis is also absent. That means this molecule is chiral and it is optically active. This isomer is optically active. Optically active. Okay. Now let's check this one. So here you can pass the plane of symmetry, right? And here C2 axis is also present. If you will pass the axis from this carbon atom, you will observe the symmetry, same stereochemistry of the molecule. That means this molecule is achiral and optically inactive. This is optically inactive. This isomer is optically inactive. Okay. Now let's talk about the last one. In last example, you can see here both the OH group are on same side and one OH group is front side. But this is the terminal one, means on carbon number 1. So that means this molecule has no plane of symmetry. If you will pass the plane, you will observe here there is a front side OH group and here is back side. That means there is no plane of symmetry is present and there is no CN axis and SN axis is present. No CN and no SN axis is present. That means this molecule is asymmetric and it's optically active. It's optically active. So if we will talk about the same four other isomer, so one more isomer will be optically active. I will show two more isomer will be optically active. I will draw here, and optically inactive molecule will I will not draw here. You can see here on if I will write here back side, all the three bonds will be on back side. That means it is optically inactive. This one similar way. Okay, and in other four isomers, two will be optically active and two will be optically inactive. So I am drawing the optically active one. You have to just interchange the stereochemistry. So you have to change the stereochemistry by just changing the wedge with interchanging the wedge OH group with dash OH group. Okay. So you can see here this is backside OH group and here we have front side OH group. This one is and this one is same. Will show the optical activity. So this is optically active molecule. Okay. Optically active molecule. I hope this example is clear to you. Now let's talk about the second one. Here I will draw this molecule. Again 5 carbon atom, but one is CH3. In previous case there was two acidic group was present. That means that's why the plane of symmetry was possible there. But here we will see here. You will see here. Suppose this is OH group. I'm not writing here wedge and dash now. We will discuss this later. First I am writing in this way. Okay. So in similar way here we have 3 stereo center. That means 2 raised to 3 isomer will be possible. That means 8 isomer is possible here. Again in same way. Now I am going to discuss the first 4. Then the other 4 you should solve by yourself. If any difficulty is there, you can discuss me in next lecture. Here, suppose this is a wedge bond. Wedge bond. Now, is there any plane of symmetry is present? Anyone? If we will pass the plane over here, we will not get the mirror image or of this molecule, this half of the molecule, because here we have acidic group and here we have CH3 group. That means there is no possibility of plane of symmetry, right? We will draw in Fisher projection. Sorry. OH, OH and OH. Hydrogen, hydrogen and hydrogen. Okay. Now, see here, if we will rotate this molecule by 180, so we will observe that there is no, we will not get the image which is indistinguishable from the original one. That means here no CN axis is present. No CN axis and no plane of symmetry is present in this molecule. That means this molecule is achiral and optically active, optically active molecule, because here we don't have any symmetry element present in this molecule. But if we will change the different isomer, we will see what will happen here. Suppose we have H, OH, OH, H, H, OH. Okay. Again here, if we will pass the plane, we have two different substituent on the vertical line. Two different substituent. That means there is no possibility of passing any plane or a axis of symmetry. So here there is no axis of symmetry is present and no plane of symmetry is there. That means this molecule is again a chiral, and this molecule is chiral and optically active. Chiral and optically active. Okay, this molecule is optically active and it's a chiral molecule. Okay, now let's draw the other isomer possible for this molecule. I will draw only 4, then other 4 you have to draw, and we will discuss in next class if you have any doubt. So in this molecule also we don't have any symmetry element present. That means this molecule is also optically active and is a chiral molecule. Chiral and optically active molecule. Then the fourth isomer is possible here. I will draw here. CO2, H, then CH3. Okay. OH, OH, H. If you will check this molecule, you will observe that all 8 isomers are optically active and chiral molecule. So these all 8 isomers are optically active and chiral. You can draw other 4 examples and you can check the optical activity of the molecule here. Okay. I hope all of you are clear for both the examples, and let's try yourself and we will discuss in the next class. Now let's move to the next question. Question number 3. Here, determine whether the marked H atom, which is Ha and Hb, are homotopic, enantiotopic, or diastereotopic. So before doing this question, we should know what is homotopic, enantiotopic, and diastereotopic hydrogen atom, and what's the definition behind these terms. So let's start with the homotopic. So homo means same and topic means place. That means same place. So homotopic atoms of group can be classified as homotopic, enantiotopic, and diastereotopic. Homotopic groups are in a homotopic ligand in a molecule are those whose position can be interchanged by rotation about a proper axis of symmetry, that is CN axis, and N should be more than 1. We will discuss with examples and it will be clear to you. So I'll write here an example of the homotopic molecule. Suppose this carbon atom is present here, then we have acidic group CO2H group, and this is a CH3. I'm drawing this way, CH3. Okay. Now let's rotate this molecule by 120 degree. I'm drawing in 2D plane, but imagine this one in 3D. I will draw in 3D. Then okay, it will be good to understand. Okay, the front side H and one is back side. Okay. Now rotate this molecule by 120. You will see here. Then all the three hydrogens are homotopic because they are related to each other and they are not changing the stereochemistry. If you are rotating by 120, you will get the same molecule indistinguishable from the original one. You will observe the same molecule if you will rotate by 120, and uh, that means here C3 axis is present and the molecule is remain same. Position of H1, H2, H3 are interchanged by one and another, but we are not getting change in the molecule. That means H1, H2, H3 are homotopic and they are related by C3 symmetry. Okay, it will be more clear to you if we will solve the example. So let's move to the example here. This is the first example. So first I will clear the other definitions also. Sorry, this is a homotopic molecule. Now let's talk about the enantiotopic and diastereotopic. Then we will solve the examples. So what are enantiotopic molecules? So a pair of ligands in a molecule are said to be a enantiotopic if they are interchangeable by SN axis. If they are interchangeable by SN axis. In question number 1, we have discussed that if SN axis is present, that means the molecule are enantiomers and they are the disymmetric molecules. So in similar way here also, if SN axis is present and they are interchangeable, that means uh, the molecule is enantiotopic. S1 means sigma plane and S2 means I. So if S1 is present, that means a sigma plane is present and S2 is I. So the group of an molecule related by sigma or I are called enantiotopic group. So we will solve the one example. We will discuss one example. I am taking here any tetrahedral molecule. Any tetrahedral molecule. This is the back side of the plane. This is the front side of the plane. So this is a chiral center, right? Now, so suppose these two are same hydrogen atoms. I am writing here X or same atom present in the molecule. So we have to find out these two X are anisotropic or the homotopic or diastereotopic. So what we have to do? We have to change one X by Y. One X by Y. So I will write here, if I will change one X by Y, what will happen? AB will remain as it is. There it is not chiral because two X are present. So I will remove here star mark and then here X, then here Y, because I'm changing one hydrogen by Y. Here and 1 and 2. So the second X is replaced by Y. Now we have to check the plane here. I will change here the other x by y. So I will draw here other x by y. So we will compare these two molecules, and here we can say sigma plane of projection is present in these two molecules. If we will pass sigma plane here from here, and then we will get this molecule, and if we will pass sigma plane here, then we will get this molecule. So that means sigma plane is present in here, and these two molecules are enantiomer of each other. So you can draw the mirror image here also, mirror image of this molecule, which are non superimposable mirror images of each other. Here you can see y and x is here. So these two are non superimposable mirror images of each other, but this one is similar to this one, correct? So that means these are two enantiomer of the molecule here. So the pair of enantiomer is x. That means x1 and x2 are two enantiotopic atoms of the molecule. Two enantiotopic atoms of the molecule. Okay. Now let's talk about the diastereotopic molecule. Diastereotopic groups are, what is diastereotopic groups of the molecule? Here I will write, if two atom or group are said to be diastereotopic if replacement of those atoms or groups by homotopic ligands uh, generates a pair of diastereomers. Diastereomer groups cannot be interchanged by any symmetric operation. So I will give one example here, then it will be more clear to you. Suppose we have al alkene, this alkene here, and two chlorine group are present on these two carbon atoms. Okay, I will draw here. Here we have two hydrogens, HA, HB. Okay, and here one Cl atom and then hydrogen. Now we will interchange this H1 and HB by HA and HB by chlorine atom. So first we will replace HA by Cl group. So here we have two Cl groups in this molecule, Cl, Cl, hydrogen and hydrogen. Okay. Now let's talk about the other possibility. Let's replace Hb by chlorine atom. So here we have chlorine, chlorine, hydrogen, and this is a double bond. Okay. Now let's see here. This is a Z isomer. This one is Z isomer, right? And this one is E isomer. So they are not mirror images of each other. They are if they are they give mirror image of each other. In that case, we can say these are enantiomer. But here they don't have mirror image of each other because they are totally different. E and Z isomer are there. That means uh, these two isomers are diastereomers, and H1A and HB are diastereotopic here. I hope the example is clear to you. Now we will discuss the question, previous year assignment question. So this is the first example. So here we have HA and HB. We will check here the symmetry and topicity of the molecule HA and HB atoms here. So if we will replace one atom by any other atom, like suppose before replacing the atom, I will pass the first we have to check the homotopicity of the molecule. So I will pass the axis of symmetry here. If I will pass C2 axis from this position, what I will get? This bromine will come this side and this HA will come front side. I will rotate it here and will draw, then we will discuss it. Okay. Now I am just rotating on this axis. What will happen? Here we will get the bromine. Here bromine, HA and HB. Correct? So if you you will see here, these both the isomer are looking similar, and they are indistinguishable from each other if we will not label the both the hydrogen atom as A and B. So that means these two HA and HB groups of the molecule are homotopic. Here both the HA and HB are homotopic because they are giving indistinguishable image of the molecule by after rotation of C2 axis. Rotation by C2 axis. That means center of rotation of axis is present here, and the molecule is homotopic. The H1 and HB group are homotopic in this molecule. I hope all of you are clear here. You can cross check by yourself, and we can discuss again in class. Okay. Now let's see the other example. Here H1 and sorry HA and HB are there, but this is a tetrahedral molecule. This is a type of a tetrahedral molecule. So as we have discussed for enantiotopic and diastereotopic, you have to change one hydrogen by other halogen atom or any other group. So I am here I am changing this hydrogen HA first, then we will change the HB. Okay, here I am just changing the hydrogen atom by Cl group. Suppose I am changing it by, or X. I can write here X, any halogen atom. Then let's change the other hydrogen atom by halogen group. X, and here it is H. Correct? Now you have to check here. These are mirror image of each other or not. So you can see that if I will pass the plane here, I will get exactly a different stereochemistry. CH3 group will be present here, and then HD group will come here. Okay, and both the other group will be on same side. So if you will compare these two images of the molecule, then you will observe here these two are nothing but the similar molecule. Just you have to rotate by 180 degree. If you will rotate this molecule by 180 degree, you will observe that this and this molecule is same. But this and this molecule is not same. That means they are non-superimposable mirror images of each other. These two molecules are non-superimposable mirror images of each other. That means they are anisotropic. They are anisotropic. That means HA and HB are anisotropic in this molecule. HA and HB are anisotropic, and the molecules are enantiomers because it's giving non-superimposable mirror image of each other. Okay, I hope all of you are clear here. Now let's see the other example. Next one. Now here you can see we have CH3 and CH3 group and OH group. If we will pass the center of symmetry, sorry, not center of symmetry, plane of symmetry. If we will pass the plane of symmetry here, we will observe that both the half of the molecules are same. That means if we will change the H1 and HB, both will give the same isomer. So both because plane of symmetry is present here and C2 axis is also present. C2 axis is also present. Sorry, plane of symmetry is present here. But if we will change the one group by any halogen atom, here I am writing here any halogen atom. If I will change the group by any halogen atom, this is OH, this is Cl, suppose it is Cl, then hydrogen, then OH, then CH3 group. Okay, and the other possibility is that we will change the H1 HA by Cl group. Cl group. This H will remain as it is. OH, H, OH, CH3, CH3. Correct? Now we have to check the both the enantiomer both the isomer are same or not. So we will see here. I will draw here mirror image of this one. Then it will be more clear to you. So if we will draw the mirror image of this molecule, OH will come this side, Cl will be here, H, CH3. This is the mirror image of this molecule. Okay. So if we will see the molecule, these two molecules are nothing but the same molecule. Just you have to rotate it by 180 in this way, 180. To whole molecule in this way by 180, you will observe that this CH3 will come this side here, and all the molecule will show the same stereochemistry as this one. So these two molecules are nothing but same molecules. But these two are not same. These two are not same, but the nothing but the non-superimposable mirror images of each other. That means this molecules is nothing but the enantiomer of each other. The both the isomer are nothing but the enantiomers, and the HA and HB present in this molecule are enantiotropic. A and HB are anisotropic in this molecule. Let's talk about the next one. Here you can see that H1 and H2, HA and HB are present on same carbon. So we will check the chirality and homotopicity, or we can, anisotropicity, whatever is present here, we will check here. So first, what we will do for diastereotopic molecule, we will interchange one hydrogen by any halogen atom. Any halogen atom. Bromine will remain same. Hydrogen, chlorine, hydrogen. Here I am changing HA by halogen atom, and then HB will remain as it is. And here I will write the other possibility. Sorry, this is X. This is H. Okay. Now we will see both the molecules. Here, if we are interchanging one hydrogen by halogen atom, the molecule are become different from the starting one. It's become a chiral. Sorry, it's become a chiral. And here also we can see these two molecules are not same. We will draw the mirror image of this one first, then it will be easy to understand. Chlorine group, hydrogen, right? Then bromine, hydrogen, then X and hydrogen. So here you will see that these two are not the same molecule, because here hydrogen is same on same side of chlorine atom, but in opposite side with the bromine atom. And here also you will see that this halogen is on same side with chlorine atom. Uh, and here the X atom is opposite side with the chlorine atom. So these two are not same. We will compare in these two mirror images also. So here we will see that this hydrogen is on same side, but it's on different carbon atom. These two are non-superimposable mirror images. They are on same side, but they are non-superimposable mirror images. But these two are not same. That means when we are changing one hydrogen atom with halogen atom, we are not observing the mirror image of each other, non-superimposable mirror images of each other. That means the molecule is diastereotopic. Diastereomer. These two are diastereomer, and the HA and HB of the HA and HB group of the molecule are diastereotopic. They are diastereotopic because they are not giving superimposable, non-superimposable mirror images of each other. So I hope this example is also clear to you. Now let's talk about this one. Here again we have HA and HB on same carbon atom. So we will replace one hydrogen by any halogen atom, and we will see the topicity of the molecule. Here, then H, and this is X, halogen atom, X. Then hydrogen here. Okay. Now the other possibility is that we will change the other H, hydrogen, OH, H, halogen, then CH3 group. Correct? CH3. Now let's compare these two isomer, or we can draw the mirror image also to better understanding. Correct? So you can see here these two are same molecule. Same. That means these two are non-superimposable mirror images of the molecules. These two are non-superimposable mirror images of the molecule. That means they are anisotropic. They are anisotropic. Ha and Hb of the this molecule are anisotropic, and the molecule are enantiomers. Two molecules are enantiomers because they are giving non-superimposable mirror images here. That's why it's anisotropic. Ha and Hb are anisotropic, and the molecules are enantiomers. I hope all of you are clear here. Now let's question. Now again we have to follow the same rule. We will change one hydrogen by halogen atom to check the topicity of the molecule, or topicity of the group present here. Again CH3, CO2H, OH, sorry, hydrogen. A will remain as it is. I am writing here halogen, then bromine. Correct? Now let's write the other by changing the other hydrogen atom, the next other molecule here. CH3, OH, X, H and Br. Correct? Now let's see both the molecules. I am drawing here mirror image as well to better understanding. H is here, H is here, X and bromine. So you can see here when we are changing one hydrogen, hydrogen A with halogen atom, we are getting this molecule by replacing A, and when we are replacing B, we are getting this molecule. But A and B are both not mirror image of each other, because here you can see on the carbon atom on which halogen atom is present is containing bromine atom, but here where we have changed the interchanged the halogen atom with the hydrogen atom, the carbon atom have OH group. So both the isomers are different here. They are not mirror images. So and these two isomer are not same here. These two isomers are not same here. That means they are not non superimposable, non mirror images of each other. That means they are not a mirror image of each other. That means both the hydrogen atom of this group are diastereotopic, and the molecules are diastereomers of each other. Diastereomer of each other, and the Ha and Hb group of the molecule are diastereotopic. I hope all of you are clear here. So thank you for your attention, and if you have any doubt, any difficulty regarding these questions or any this topic, you can discuss with me in next lecture, and we will discuss in detail each and every question. Thank you for your kind attention.